Morning ma'am, my name is Nandini. I am from CSC B section. Subject name is Advanced Data Structures and Algorithm Analysis. Subject code is 23 CSC 302. And today my topic is Enquine's problem. The outline of Enquine's problem is Introduction to Backtracking, Historical Background, Definition of Enquine's problem, Problem Constraints, Example of Enquine's problem, Algorithm for Enquine's problem, Advantages of Enquine's problem, Application of Enquine's problem, and Conclusion of Enquine's problem. First, we are moving to the Introduction to Backtracking. Backtracking is an algorithm technique used for solving problems incrementally by exploring possible solutions and abandoning those that fail to satisfy the constraints of the problem. It involves the following key aspects. We have some key aspects in backtracking. Those are incremental approach, recursive exploration, and first we are going to the incremental approach, and the algorithm builds candidates for solutions step by step, one piece at a time. Recursive exploration is the second key aspect in backtracking. If a partial solution can be extended to a valid complete solution, the algorithm continues, otherwise it backtracks to the previous step and tries a different option. Next, third one is pruning. As soon as solution is found to be invalid, not satisfying the problem's constraints, the algorithm eliminates that path from further exploration efficiently, pruning the space. Exhaustive search is the fourth key aspect in backtracking. While backtracking systematically explores the search space, it may not necessarily examine every possibility, especially when optimizations like constraint propagation are applied. In sense, backtracking is a refined brute force approach that intelligently navigates the solution space, making it particularly effective for problems involving combinational structures such as puzzles, games, and constraint satisfaction problems. Backtracking is a brute force thing. It gives lots of applications for us in computer applications. Next, we are moving to the historical background of backtracking. Backtracking originated from early combinational mathematics, where mathematicians sought systematic methods to explore permutations and combinations. Its formalization as an algorithm technique was significantly advanced by Donald Knuth in the 1960s in The Art of Computer Programming, where he demonstrated its effectiveness in solving problems like the Enquine's problem. And then throughout the 1970s and 1980s, backtracking gained prominence in artificial intelligence, particularly in game playing and decision making. Over time, various optimizations were developed to enhance its efficiency, and today backtracking is a foundational concept in computer science education, widely used in solving complex combinational problems. Next, definition of Enquine's problem. The Enquine's problem is a combinational puzzle that involves placing Enquines on an n by n chessboard in such a way that no two queens can attack to each other. The objective is to determine all possible arrangements of the queens on the board that meet this requirement, making it a classic challenge in algorithm design and problem solving. The problem not only serves as a theoretical explosion in mathematics and computer science but also has practical applications in areas like optimization and artificial intelligence. This is the definition of Enquine's problem. Next, we are going to the problem constraints in backtracking or Enquine's problem. In the Enquine's problem, using backtracking, the main constraints are there are three constraints in backtracking Enquine's problem. First constraint is a row constraint. No two queens can occupy the same row. Each queen is placed in a unique row as the algorithm progresses. Column constraint. Column constraint is the second constraint in NP's problem using backtracking. No two queens can be in the same column. The algorithm tracks occupied columns to prevent placing queens in the same one. The next constraint in queens using backtracking is diagonal constraints. No two queens can be on the same diagonal. This is checked by ensuring that for any two queens at all positions R1, C1 and R2, C2. R1 is row 1 and C1 is column 1 and R2 is row 2 and C2 is column 2. Major diagonal is R1 minus C1 equal to R2 minus C1. Minor diagonal is R1 plus C1 equal to R2 plus C2. These constraints guide the backtracking algorithm in systematically exploring valid configurations while pruning invalid placement. Next, the example of n-place problem. I'll take n value as n. So in chessboard is also n cross n. So the chessboard is I take 4 cross 4 chessboard. First we kept queen 1 in first row first column, and then next queen we kept in second row second column. A diagonal constraint is applied, so we don't kept the second queen here, and then the third queen kept in third row. There is no constraint is not constraint is not applicable here, so we place the queen 2 here, and then next here we kept queen 2. The queen 3 is not possible kept anywhere in this chessboard, so that's why we kept queen 2 in this fourth row and fourth column, and then we kept queen 3 in this third row fourth column, and then fourth queen we kept. So that's row constraint is applied, so that's why we kept queen 1 in this first row second column, and then queen 2 is kept in fourth row second row and second column, and then queen 3 is kept in first row third row and first column, and queen 4 is kept on third row and fourth row and third column. And then the final solution for n queens problem for n equal to 4, the 14th problem solution is 2413. And then algorithm for 4 queens problem is place the queens column wise, start from the leftmost column. If all queens are placed, return true and print the solution. Else try all the rows in the current column. Check if queen can be placed here safely. If yes, mark the current cell in solution matrix as 1 and try to solve the rest of the problem recursively. If placing the queen in above steps leads to the solution, return true. If the placing the queen in the above step does not lead to the solution, backtrack. Mark the current cell in solution matrix as 0 and return false. If all the rows are tried and nothing works, return false and print no solution. And then advantages of 4 queens problem is conceptual understanding. It introduces fundamental concepts in backtracking, algorithms and problem solving strategies, making it an excellent teaching tool for computer science students. Algorithm development, solving the problem can help in developing and understanding algorithm for more complex combinational problems. Mathematical insight, the problem encourages exploring of combinational mathematics as it can be framed in terms of graph coloring or constraint stratification. And then applications is algorithm development. It develops algorithm very easily through backtracking. Artificial intelligence, the problem can be used as benchmark for testing AI algorithms, and robotics also we use n-queens problem using backtracking. It is very useful like algorithm development, artificial intelligence, robotics using backtracking is very simple and easy technique. And then conclusion of my topic is the 4 queens serves as a foundational example in combinatorial optimization, demonstrating key concepts in algorithm design and constraint stratification. It not only provides a platform for teaching backtracking and recursive algorithms, but also has a real-world applications in areas like scheduling, resource allocation, and robotics. Overall, the 4 queens illustrates the vital connect between theoretical challenges and practical applications. And finally, thank you, ma'am.